Let's talk about the EaganMatrix tuning grid interface. This allows you to create and load your own microtonal scales or other kinds of tunings that you want using this interface that's been around for a long time, but until now only the pitch table editor, the PTE third-party tool, has really been used to support this function. But now that we have overlays, it's time to lay out exactly how you can program this yourself if you want to. I've created, for example, a tuning interface for the Electro 1 controller, but there's no reason why you can't create your own because the interface is rather simple. Let's talk about that, say a few things about how you can program your own, and in general talk about microtuning and the Osmos and the continuum. Or you can run this on an EaganMatrix module or micro or Continuum Mini as well. Now let's start by talking about the tuning control functions that already exist, most of which are in the editor, some of which are on board on the Osmos or Continuum. And these fall into two categories, one which support both the Continuum and the Osmos, and the other are Continuum-only functions. So first thing, transposition. This is not really supported on the Osmos or on the Continuum directly, but you can program it yourself using CC8, the octave shift CC, or you can do now a matrix poke using an overlay matrix operation that resets middle C. This operation is also available in the editor where you can reposition middle C. Fine-tuning control, this lets you set your current tuning up and down up to 60 cents. This is available on board on the Osmos as a menu control function. It's available using CC10, which you can set a value of 4 to 124, with 64 being the midpoint that has no tuning offset applied. Then there are the standard tunings that you can select from. So CC51 can be used to set a just tuning if you set it to a value of 60 to 71. Tuning grids, those are what we're going to be talking about here today. Those can be set using CC51, channel 16 that is, on CC51, set to a value of 80 to 87. This sets one of the 8 tuning grids that can hold a micro tuning that you can download yourself. You can also reset to equal temperament anytime you like by CC51 channel 16 setting a value of 0. Then there are all the custom tunings that we'll talk about today that you can set using the pitch table editor now, or the new Electro 1 NK2 Retune app, or your own app. Just note that tuning grids are broken in 10.5.2 DSP firmware, and you'll have to either run on 10.09 previous DSP firmware to load your own tunings, or wait until the post 10.5.2 release is out. There are a few continuum-only operations that will apply to pitch. The end of tunings are really intended to rescale the continuum surface equal division of an octave. Now on the continuum surface, you might not be able to hear this unless you fully quantize, you fully round, and so the rounding functions, CC25 on channel 1 for round rate and CC28 for round initial, are always available, and those are on board the menu system too. They really have no meaning for Osmos because Osmos is a fixed key controller. If you try and set rounding on the Osmos, it will actually round within the key itself, and that really is not what this was meant to do. So these are the general functions that you have available to you. They're available in the editor too. This little control sets middle C to a different value, so you can transpose by moving this in the editor from its default C position to wherever you want to transpose. Here we can set our rounding options. We can set the jump to a tuning grid with an initial set. We can set your tuning options, your equal temperament, your end divs we talked about. You can actually set more of these with a CC. There are only these available in the editor. And then you can have your just tunings, and most importantly, you can set your tuning grids in the editor using one of these options, and of course using the CCs we just talked about. So now let's talk about how you can actually program your own tunings. Let's start by looking at the standard MIDI table. Here, MIDI note values 0 to 127 are associated with pitches that you normally are used to. And in our default mode, when you boot up your Osmos or your Continuum, you will be in equal temperament if you haven't changed anything. So each one of your octaves, starting at MIDI note 0, 0 to 12 the first octave, 12 to 24 the second, and so on and so forth until you get through all of your 127 values, which ends at a G9. Those values in equal temperament are going to be associated with a cent offset. In equal temperament, every semitone is going to be 100 cents away from the next one. And that's basically the main math that you have to understand. We're working in cent offsets when we apply our tunings. Of course, in equal temperament, every octave has the same cent relationships. Now, that doesn't mean you have to program a tuning to do that. You can program your tunings to have all kinds of different relationships. So that's the first thing to understand. Now, the next thing is to look at how the EaganMatrix deals with these MIDI notes. I'm going to simplify this for this presentation. You'll be able to do more complex things than what I'm talking about, but probably 90% of what anyone wants to do is going to be related to what I'll talk about today. So in the EaganMatrix, you have a from note 0 to 127 that are mapping to MIDI notes, and then you have a to note, again 0 to 127. Your from note is going to map to the expected note that you push on your Osmos, or you play with a MIDI controller or press on the Continuum template. The to note is the note that actually comes out in relationship to your from note. Now, if your from note's the same as your to note, that's going to most times just be your normal equal temperament. So we have a from note, we have a to note, and now we have offsets. So this is actually a representation of the tuning grid interface. There's going to be a from note, then there's going to be a 14-bit from offset that's going to be split programmatically, a most significant and least significant LSB part. And then you're going to have your to note, and that is also going to have a 14-bit MSB LSB offset. Obviously, the 14-bit offset is going to be programmatically split into two 7-bit MIDI values, MSB and LSB. And for each one of our MIDI notes, we can apply one of these from and to records. Now, you don't have to always send all 128 of these values, but for our discussion, we're going to do that. We're going to totally rescale all the values. There are ways to do this with less values, but I think it's simplest to just look at how we totally rescale the entire MIDI set to a new tuning. And as you can see, the lower notes in my C-1 octave, some of those lower ones you're not even going to be able to hear. The lowest note on the piano doesn't start until A0 down here. So as we see, you may want to offset your notes so that you don't even have these bottom ones being played. There are reasons why you'll want to do that. And of course, the actual pitch that's going to come out when you're retuned, it may be your actual expected MIDI note frequency, but more than likely it's going to be some frequency offset from that to create the tuning that you want. Let's go through and see what we have to do to actually change a tuning. We're going to use the scalar representation format here because that's pretty easy to understand. And I'm assuming that most people who want to write their own microtuning interfaces understand scalar. So in our default equal temperament, we have 12 notes. We're going to be using a 12-note tuning. We can create higher level tunings, but most of this discussion will center on rescaling 12 notes. That's what most of your standard MIDI controllers will use. And as we saw, in equal temperament, each one of my 12 notes is 100 cents off from the next until I get to my 2-1 octave, octave being twice the frequency, and this is going to just be replicated across your full MIDI interface. Scalar representations can either be in cents, as we have in our 12-TED example, or they can be ratios, or they can be a combination of cents and ratios. So let's retune, let's say, our Osmos. Instead of playing my 12 chromatic notes and have equal temperament come out, let's retune them so that when you play a chromatic scale, you're going to get a 12-tone Pythagorean scale coming out. So the first thing you're going to want to do is take your ratios or your cents specification and create a table for all 12 of your notes specified in cents. You can just use that value. If you have ratios, you're going to have to use a formula down here to create cents from your ratio. Now I've also included, if you use Excel and you type in some text for ratios, this is a formula that you can plug in, and that will take that ratio and it will convert it to a value, and that value then can be plugged into this formula to create the actual cent value. And once we have those cent values, we can then compare them to our equal temperament value and see for each one of my 12 notes how far off, what's the delta between the note that I want and the equal temperament value, because our offsets are always going to be based on our from and to MIDI values, which expect equal temperament semitone values, and the deltas that we apply for our offsets are going to be a percentage of the semitone off from what the expected equal temperament value would be for that position. Now, as we see here, some of the values are positive offset from the equal temperament value, and for some tunings, some will be negative. For some tunings, they'll all be positive. For some tunings you want, they might all be negative. For some, they might be a combination, as we have here. But the important thing is, when we retune our offsets, they always have to be positive offsets from our two notes when we make our tuning. That means I have to somehow take these negative offsets and work them into positive offsets. Well, how do I do that? Well, we can see in this table, which is the same table, if I have a negative offset from my expected equal temperament value, what I can do, because that offset is going to be, say in this case, 294.14 cents. So instead of applying that as a 2 offset from my 300 place note, my from 300 cent MIDI note, I will apply that as an offset to the second 2 note place, my 200 cent offset, and instead of a -5 offset now from 300, that would be 94.14 cent offset from 200. And this is how you have to go through your tunings. I hope this was explained well enough to map your 2 note to your from note and give it an offset that will get you to the expected cent offset from equal temperament. Now let's go through and create the complete data set we need to send to the DSP to install the desired tuning. We have our tuning defined in cents. We have the related equal temperament cent values. We compare those. We get our offsets. If that offset is positive, I just use it. If the offset is negative, I have to do my 2 note adjustments. And an easy way to get your 2 note is to simply use a formula. Take the int value of your tuning and divide it by 100. And that'll throw away the remainder because we're not doing any rounding in this operation. And that should give you your 2 note with the offsets, which again all have to be positive. If the offset was negative, I just add 100 to that to get the positive related offset. Those offsets have to be turned into percentages, multiplying by 0.01, and that'll get you a percentage. And that's going to be the percentage of a semitone that's going to create the tuning for that tuning slot. But we're not working in terms of actual cents in the data set. We're using 14-bit fixed precision numbers. Well, 14-bit number can have 16,384 values, And so what I'll do is I'll take my percentage, and I'll take a percentage of 16384, and that will give me a 14-bit precision value of cent offset that I need to apply. But I'm not sending a 14-bit MIDI value, I'm sending two 7-bit MIDI bytes. So I have to take my 14-bit value and strip off the most significant MIDI byte and the least significant MIDI byte. An easy way to do that is to just take the int of your value divided by 128, and that'll strip off the top 7 bits. Then I can use mod of the value and 128, and that'll strip off the bottom 7 bits, and that'll give me my 2 offsets. You could also use bit shifting and ORing in your code to do the same thing, of course. In a spreadsheet, it's easier to do this. Then I have my from offsets, and for the purpose of this discussion, the from offsets are all going to be 0, because I'm going to base everything on my MIDI note frequencies. It doesn't have to be. I could, if I wanted, add an offset to the base from value. Let's say I wanted to start everything shifted up a quarter tone. You could do something like that. But it's easier to just keep your from offset 0 and do everything in terms of 2 offsets. I find at least. So that will now create all the data I need to send to the DSP. One thing to note, of course, I'm going to iterate these values from my beginning MIDI note right up to the last MIDI note for this example. Obviously, each octave is going to maintain the same cent offset relationships. The only thing that will change are the from and the 2 notes, which iterate up through the full MIDI range. But you don't have to do that. If I wanted to, I could create a different tuning for every octave. Perfectly doable. But this video mostly is going to use these standard tunings that are applied iteratively for the whole tuning set. I could have some cent offsets that are more than 100 cents off, even 200 or 300 cents. In that case, my 2 notes could actually be greater than my from notes. In this case, I have a value in the 10th slot that is supposed to be 900 cents, but it's actually 1,017 cents. So I will use the 10th MIDI note, that is the 1,000 slot, and I'll offset that by the 17.59629. Using this int of the value divided by 100 still gives me the right value. Now what do we actually have to send to the DSP to create the new tuning? The first thing you'll do is you'll set the tuning grid, send on channel 16 CC109 with a value of 80 to 87. That will set one of your 8 possible tuning grids to accept the data that will follow. Then you'll send your tuning data that we just created. To do that, you send CC38 for each one of the 6 data sets in the record that you'll send. CC38 with a value of 0 to 127 will be the base from note. Then send CC38 with your MSB value, 0 to 127 of course. Then CC38 with your from LSB value. Then you'll send CC38 with your retuned 2 MIDI note value. Then you'll send CC38 with your 2 MSB, and finally CC38 with your 2 LSB. So you'll send 6 CC38 values for each of the tuning records you want to send. If you want to change all 128 values, you'll send 128 of these records to retune the entire MIDI dataset. And finally, you will send on channel 16, all these CC38s are also on channel 16. You'll send CC109 on channel 16 with a value of 101, which will write all of that tuning data to the tuning grid flash for that location. And of course, if you have multiple tunings, you can iterate this over. Select another grid, send your tuning data for that, and you can do this up to 8 times if you want to fill all of your 8 tuning grids. Then of course you need to send, before you play that, a CC51 to actually select the tuning grid that will be active and then you can perform your tuning. Here's some example code that I use in my Electro One MK2 retune app that has a lot of retuning options. You're going to need, of course, a MIDI library that sends CCs to the appropriate either DIN or USB interface for your Osmos or Continuum, EaganMatrix module, Micro, or Continuum Mini, whatever you are retuning. You may need some poly aftertouch messages if you want to do more sophisticated things in terms of your overlay, but to set a tuning, you just need to send CCs. So I'll start by sending my MIDI control message to select the grid that I want to retune, CC109 channel 16. Then I'll iterate from a starting index to an ending index. I set everything in arrays in my program. That's probably a good idea for you to do too. But however you want to program it is fine. I'll send my set of 6 tuning records using CC38 with the from offsets, 2 offsets we just discussed. Then when I'm done sending that data for that tuning grid, I'll send the finalize message, CC109 on channel 16 with a value of 101 to write that tuning to flash. And here I send a control change CC51 on channel 16 to set my current grid for performance. After this, I should be able to play and that new tuning should come out. A few other things to think about. What if I want to retune something with more than 12 notes? Let's say I want to tune a 17 EDO scale. To do that, I do the same thing. I find, in this case, a sent value offset. I'll apply that iteratively, getting my 2-note values and MSB, LSB offsets. I'll send the 17 values, and then I will be back to my octave, so my offsets would be 0 at the bottom there. So you can send anything you like as long as you map your offsets to the desired tunings. You can create a 17 EDO, a 31 EDO, whatever you like. And you don't have to iterate at the octave. Mixed tunings, as we said, there's no reason why I can't keep, for example, equal temperament up to some MIDI note value. Here, MIDI note value 60, C4, and after that I can send my retuned values. In this case, I have equal temperament up to C4, and after that I have a Dowland loop tuning applied. In fact, you can have a split point in your code, like I do in my app, where I can set one tuning beneath the split point, another tuning above a split point, and if the split point has some middle value that's left the same, I can have 3 different tunings set. And as we said before, if you want to, you can set a different tuning for every octave if you like. It's very, very flexible this way. But you just have to understand the from, to, MIDI associations that you need to program this in the EaganMatrix. Finally, you don't have to have a tuning that iterates at the octave. You could create, for example, a Carlos alpha tuning that has a sent offset that just keeps being applied, and that offset doesn't repeat at the octave. Perfectly acceptable. All you need to do is calculate your from notes, your to notes, and the associated sent offsets as 14-bit entities. Finally, one thing to take into consideration is that if you create some higher order scales, say EDO 22, you're going to have to take account for the compression that will take place if you plan on playing this using a standard keyboard controller versus, say, an isomorphic controller that has a much fuller range that's easier to manipulate. Because you can see here the standard octave placement C1, C2, C3 is going to be all off if you're going to use a half step per step of the EDO 22 scale. So here C0 is going to be offset 22 notes from its initial position, and 22 notes after that you'll get another C, and 22 notes after that you'll get another C. But look where those fall on the keyboard. You don't get until around C4 that you would expect coming out in standard equal temperament tuning. You're going to be less than C2 coming out on the keyboard playing your EDO22 scale. So what can you do there? Well, you can offset your from notes and your to notes as you see fit to raise the output of the MIDI notes on your scale. What that'll mean is you might not be playing anything on the lower octave or two as you raise things up, but you don't hear much down there anyway. So on these larger EDO-N options, think about offsetting your from notes, your two notes, one or the other or both, to put yourself in a better playing position if you actually plan on playing these scales on a keyboard or some standard MIDI controller. I should also mention, to wrap things up finally, that when you load a new preset, whatever tuning is set in that, be it equal temperament or just or one of the tuning grids, that will take over. But there is a way for you to maintain a tuning across presets, and you can do that in MIDI and global settings in your editor. Put surface processing to preserve from its normal replace option. So if you preserve surface processing, going from one preset to the next, your tuning will be preserved. Also in this, you can see the fine tune option as well. So that's the last tip I have to give you here. Good luck in your retuning programming.